intro. Yeah, as mentioned, I'm Quentin Anthony, so I lead the AI engineering efforts at Zyphra, and I'll talk a bit about that now. So today, yeah, me from Zyphra. So today, who is Zyphra and who am I, and what am I talking about today? So Zyphra is a full-stack open superintelligence company. It's a big mouthful, but today we'll be talking about Inference Cloud and the Inference Cloud product that we're launching, sort of a launch preview today. So first off, that's on the base is Zyphra Cloud. So we're moving towards providing to users bare metal GPUs, as well as on top of that, our own Zyphra models. So we have our own proprietary models. Sorry, not proprietary, open source, but proprietary meaning our own recipe, our own model architecture, trained fully on AMD compute end-to-end from pre-training to RL. And they're served alongside the most popular open source models of today. This is like DeepSeek V4, DeepSeek V3.2, as well as GLM and Kimi and so on. And all of these serve the top layer of the stack, the Maya agent that we're working towards. The Maya agent ideally does a lot of different things, and to do a lot of different things well, you need a lot of different models. So these models will come from open source. Some of them will be our own, some of them will be external, but all served by this Zyphra Cloud. Everyone talks about AI being a layered cake, and this is the one we're baking. So a bit more into the actual Zyphra Cloud that I'm talking about today and that we're previewing is first off is Inference. So actually serving open models, our own and others, and that requires a lot of kernels and algorithms, a lot of routing across different models that we need to get sort of finely tuned within the company. Compute will be coming soon. That's what I was mentioning earlier on providing bare metal for users that are more advanced, want to do their own setups. Agent environments are becoming bigger, so we want customers to be able to focus on their own specific reinforcement learning recipes and also productize all of the in-house reinforcement learning setups that we've been able to really finely tune today, so that our customers doing reinforcement learning and agents and sandboxes can just focus on their specific data recipes and let us handle the frameworks and the compute. Which is the last point I mentioned. So post-training and RL being productized, all within the cloud, all powered by AMD first. So then who am I? It's really nice to be able to say, yeah, we're doing everything. We're across the entire stack, but I need to sort of back up who we are and why we've been working so hard. And while the hardware is well suited to these tasks I'm saying, how are we well suited to the hardware? So I lead the performance engineering team at Zyphra, so we optimize the training and the throughput. So all of the kernels that I mentioned earlier, all of the low-level technical details that I'll be getting into, just at a high level within the talk, I lead that day to day. We pre-trained Xia 1 base, which is an 8B open source model, on an AMD cluster of 1024 MI355X GPUs. We've scaled up quite a bit since then, but we learned a lot about AMD hardware, and this is what ours looked like. This, at the time, was 8 MI300X GPUs per node, and it takes a lot to make that thing go burr. It takes a lot to make that produce end-to-end a full model. The entire stack we had to port over from inference to training, and within training from pre-training to RL. Quite difficult, but now it's time to reap the benefits of this in-house knowledge all around the AMD ecosystem and productize the inference part. So we are an AMD first inference cloud. What does that mean? So current available models are sort of the most popular ones that we were seeing at the time. We kind of want a focus. You have to decide. Do you want to do kind of all models fairly well, or a few models that you go really deep on and produce as fast inference as possible? We chose the latter. So we are choosing the big MOEs that are very amenable to AMD hardware. They're very large. There's a lot of memory pressure. So GLM 5.1, DeepSeek V3.2. We were hoping to get V4 a little earlier, but DeepSeek didn't let us know before they released, which makes sense. And then Kimi K2.6 with DeepSeek V4 coming soon. These are all optimized for AMD MI355X with novel parallelism schemes, new kernels, and then also taking the existing kernels and tuning them. So we're not really interested in rebuilding any wheels, so we just take this open source stack from AMD and we tune those kernels for, say, attention and such to make them work for these specific models and use cases. This is all powered by TensorWave Compute. We love TensorWave. They didn't pay me to say that. And we look forward to scaling up the inference cloud with them. Okay, so let me get a bit more into why AMD GPUs are great for inference. So first off is the principal benefits of AMD GPUs is VRAM quantity. So the amount of memory per GPU is huge. That makes my job a lot easier. I can fit people's models in a lot fewer GPUs, even though like AMD is my favorite bill to pay, like if I have fewer GPUs, then I can serve more users on them, and I can lower my cost to more users and make their lives easier. Long context and large KV caches are becoming super important for agentic workflows. So everyone is trying to have these very long running sessions with a lot of KV pressure, with very long context. Entire code bases are going into Kimi, and I can serve a lot more of them on fewer GPUs on AMD. There's also VRAM bandwidth. So as much as I spend time on things like diffusion and speculative decoding, which I'll talk about in a bit later, the more bandwidth I have, the easier my job is to produce whenever we are bandwidth bound. And even in the compute bound kernels, they're easier to write when I have more bandwidth at my disposal. So there's also MXFP8, there's all these different data types and quantizations. There's much more flexibility compared to prior, say, MI300 and other prior GPUs where I can quantize the model in very fine-grained and unique ways that just fit every single block so that I get the full accuracy every single time. So there's a lot of quantization schemes that we're working on, all supported by the MI355X low-level data types. And then lastly, while these make AMD GPUs really good at everything, they absolutely excel at a few specific cases that are becoming hot today. So these are largely agentic use cases, so huge KV caches like I was mentioning, AMD GPUs really excel at, as well as serving huge models. So 1 trillion, 2 trillion, and beyond in the coming years. I'm still able to serve them on these AMD GPUs. I can serve them on less. I have more serving headroom. AMD GPUs are doing the job. So let's dig a bit into an example. It's really nice for me to say they're good for agents, but what does this actually look like, and why should you care about it? Let's take Kimi K2.6, so about 1 trillion total parameters. They're all native int4 already, so about 500 or so gigabytes of VRAM for the model replica. We always have some overhead, say 80 gigabytes of activations and CUDA graphs and so on. But going beyond a single node is stepwise in complexity for everyone. So for us, the inference providers, it's stepwise to go from 1 node to 2 nodes hosting a single model. Going across that node boundary is really expensive. So it increases latency. I don't want to do it. So I want to fit my model within a single node. For users, going across, both the metrics are worse because now you're bottlenecked by the internode interconnect. But you'll also be more often on the queue, so there's fewer replicas of the model on the same fleet of GPUs at a time. So being able to fit my model on fewer GPUs is in my and your best interest. Okay, so let's see. So as a concrete example in sort of a synthetic preparation benchmark, these numbers are a bit lower. If you do like on a full serving framework at 256K context, and a B200 system can support about 100 agents within a node, and we can about double that on MI355X at about 180. So far, more people on the same hardware, and then I have more flexibility to add hardware. I can't add hardware, immediately. I have to wait until it becomes available to me. So this gives me more headroom and allows me to serve more people. Okay, so this also translates to actual metrics. So again, on my synthetic test, any context length, we can store a lot more users' caches. So it's not just at the 256K. If we have a lot of small, like say 50K requests, we can serve a lot more of them on the same node. And then user metrics will also quickly deteriorate once caches start thrashing. So I'm talking about these long-running, agentic, many-turn inference workloads that people are running. If you start getting evicted from your node, from your KV cache within the GPU VRAM, then you will very quickly see degraded metrics across the board. And your agents need the lowest latency possible, and AMD GPUs make that much easier for me and for you. So this is true across the board, and it's becoming more true. So as we go to DeepSeek V4 and beyond, models are getting really big. And that serving headroom is becoming more and more important. So for all of our models, not just Kimi, this is an important thing that we keep in mind and we serve to users. So I've told you a bit about why we're launching and why the AMD hardware is good for inference, but now why are we good for the hardware and why are we doing this in the first place? So as I mentioned, we started as sort of just a training lab. Now we're sort of emerging into two pillars sort of Zyphra research, where we still produce Zyphra-specific open source models that are meant for agentic inference, continual learning, memory, and everything else. And then today, we're talking more about the Zyphra Cloud itself. And so how does the research historical part of the company and that column inform this new column of Zyphra Cloud? So parallelism schemes, within the paper I mentioned earlier when we trained Zaya 1, we found first that AMD intranode fabrics are point-to-point. They're not switched. And that means the more GPUs that you use within a collective operation, communication operation, the more bandwidth that you have at your disposal, the more links you can use, because they're all point-to-point. That means instead of ring attention, where you just have this revolving ring of your attention operation, and you're limited by the point-to-point fabric, you should instead use tree attention. So reformulate the distributed attention operation in terms of collective communication, get everyone talking at once, instead of just two pairs talking at a time, is able to significantly increase our metrics for both latency and throughput. So this is one Zyphra-specific optimization that we learned from training. Another one that will be announced a bit more formally on Monday is tensor and sequence parallelism folded. So instead of having separate axes, one for the model weights and one for the sequence, so your very long context 256K inputs, you fold them into one axis, and you say that every single GPU gets an equal slice of both the weights and the sequence, so that we're able to much more efficiently serve models. We can serve them again on fewer GPUs. Each GPU is responsible for a narrower slice of the total model, and they have to communicate less often. So this is another one, just trying to show why we're able, like everything within the Zyphra sort of software ecosystem, everything that we're building sort of feeds into each other. So we're able to do training and inference well, and both benefit the other. So more on training-informed inference and how we're going to be adding new features to the inference cloud based on what we've been learning is parallelism schemes I already mentioned, so tree attention and folded tensor sequence parallelism. Another one is forward pass kernels. So everyone likes to talk about kernels. We've been writing a lot of kernels at Zyphra. We've been writing a lot of forward and backward kernels for training, right? Forward kernels now we're focusing on as well, and every single forward kernel that we write is able to sort of build upon this knowledge base that we've developed over time. And that direction also goes in the opposite direction. So every kernel we write for, say, DeepSeek is able to teach us new lessons about how we can train our own models, and very viscerally shows us where the bottlenecks and challenges are for serving people so that we can train our own models to be also just as efficient. So that also leads me to model quality. So quantization and speculative decoding, we're sort of uniquely positioned to hit this because of our training background. So we know for quantization, models are very sensitive. You can't just turn them into FP4 and feed them to everyone. The accuracy tanks. So we're able to kind of really boil down the essence of what makes a good quantization and how to preserve model quality. It's also speculative decoding. So speculative decoding happens when you're trying to train a model to predict what next tokens are going to be produced, and we're able to train those better than some competitors because we're so used to training models. But it will be more and better speculators are on the horizon, and they can also be much bigger because we have more VRAM accessible to us, much bigger speculators that are more accurate. I mentioned a little bit earlier, but this inference informs our training ambitions as well, so we're not giving up on training. Experience in inference helps us train better models that show us where the bottlenecks are. Backward pass kernels I already mentioned, quantization-aware training I already mentioned, and then again, RL inference engines will be a major product that we'll be targeting very soon. And all of this feeds together in there. Both an inference engine and a training engine are needed for a reinforcement learning product that we intend to provide. Okay, so looking forward. Where are we moving now? Where are the next optimizations we intend to do? So we have newer and better models are coming out. DeepSeek V4 is something that we're about to be working very hard on now that it's been dropped. Larger and more powerful speculators, as I mentioned before, so having better draft models, larger draft models, and then novel quantization methods that also preserve accuracy. We're working towards very hard here. All of these to serve the cloud, all of these in order to provide on the API, and will serve as inference engines within the RL product. So thank you. That concludes my talk today, and I'll talk to you later. Thanks.